Just a reminder, open space on Helping Kids Code with David and Whitney tomorrow at 11. Cool, so Alex. Alex is the founder and head of data science at NumberBoost, which is a data science consultancy. So if you see anything you like in this talk, you can, well, ask Alex whether his company can do some of this for you. Alex has been very excited about data science for a long time. He organizes the Cape Town machine learning and deep learning meetups, and was part of the organizing committee, well, actually chaired the organizing committee for last year's deep learning in DARPA-X. And he's here to talk to us about deep neural networks for video applications. Take it away, Alex.
Yes, thank you, Simon. And thanks, everyone, for staying here so late in the day. I know we're starting a bit late, but I'll try finish on time. And I'll stick around for extra questions later if you have any. So I'm going to be talking about deep neural networks for video applications. And as Simon said, I run a data science company called NumberBoost. We've won a bunch of awards, and we organize a bunch of meetups and community events around machine learning and deep learning. So, hands up if you've ever built or used a deep neural network before for anything. Yo, that's a lot more than, I spoke at PyCon 2 years ago. It's a lot more than 2 years ago. Okay, keep them up. If you used a deep neural network for something computer vision related. A lot of the same hands are up, because the first sort of application of deep learning that really worked was computer vision. OK, keep them up if that was video related and not just running models and images. All right, still a couple hands up, but most of the hands go down. And it's not surprising, because video is a lot harder to process than images. But there are all kinds of exciting things you can do with video. Now, a lot of people are kind of scared of AI. The message I have for you today is don't be afraid of AI. And I'm sure some of you have seen this great Arnold Schwarzenegger classic. My audio is not working, so I'm just going to freestyle. But deep learning is up to all kinds of things these days. So you may have seen this. This was doing the rounds on Twitter a couple months ago. None of those faces are real. Those are all sort of hallucinated by a deep neural network. And there's a fun website you can go to, This Person Does Not Exist, where you can just see as many fake people as you want. You can kind of tell if you look at like the eyeglasses frame on the one side versus the other side isn't symmetrical, or if you look around the eyes or the teeth. But things are getting better really quickly, and we live in scary and really cool times. So Ian Goodfellow, one of the researchers who came up with these generative adversarial networks that are used for these sort of fake news or deep fakes applications, had a great tweet showing progress over time. And you can see how much better things are going year by year. And what's interesting is the way that these models generate images is they use this latent vector space that encodes semantics and lets you do all kinds of interesting things. And we'll talk about ImageNet later, but you can interpolate between classes in this image space to do, again, crazy and interesting things, and useful things. So this example of this pix-to-pix generative adversarial network shows the original black and white film, this movie Rear Window at the top. At the bottom is a colorized version that was done by hand, frame by frame, painstakingly, I'm sure. And the one in the middle is the output of a deep neural network that was trained on taking color movies, making them black and white, and then learning a model that maps black and white into color. And similarly to mapping black and white images into color, you can map low-resolution images into high-resolution images. And of course, you can generate as much training data as you want, because you can just trivially create low-resolution versions of images. But neural networks do really well at sort of hallucinating the details of images, given a large training data set. Twitter acquired a company that did this for a lot of money a few years ago. That was 3 years ago, but that screenshot's like 1.5 years old. So things are moving really quickly. And it's really useful because you can send a low-resolution version of an image or a video and have a model on a device and then use the model to increase the resolution on the device instead of needing to send a high-resolution version, which uses lots of bandwidth. You may have also seen some of this Prisma stuff where you can combine an image with an art style to create stylized outputs. Well, that works on video as well, because a video is really just a sequence of images, and so you can run a model that's meant for images on a video. And rather than just naively doing this on the video, you can run a pose detection model to sort of make people who can't necessarily dance do all kinds of things. So you can see the hand sort of disappears in that output, but it's not going to be long until you can't tell the difference between the output of a deep neural network model applied to video and a sort of real version. And again, there's all kinds of interesting applications of this stuff, but it's also potentially scary. I mean, I'm less scared than a lot of people of AI taking over the world because it took us like 5 minutes to get a projector to work, and people were worried about AI taking over the world. But yeah, I mean, there are interesting implications of these things. Again, I don't think the sound is playing on that video, but it's essentially a video of Obama saying the same speech where all 4 of those videos are synthesized from an input video. And if you do a sort of poll and ask people which one they think is real, people will give you answers, but none of them are real. Those are all generated by a deep neural network. Similarly, here's this Chinese news anchor that's completely generated by deep learning, and it's got this sort of like corny demo where they talk about, no, I can do facial expressions and I can do hand movements, but I don't think a lot of people would think that that's fake when they first saw it. Similarly, deep learning is being applied to all kinds of scary surveillance stuff, especially in China. So this is this company SenseTime that I think at one point was one of the most valuable startups in the world, probably still is. Similarly, in China, here's a model that uses really just high-resolution cameras and object detection models to capture faces at very high resolution. And if you have these cameras spaced throughout a city, you can then track people's movements throughout a city and do all kinds of scary totalitarian things. And there's all kinds of like interesting sci-fi reactions to this kind of thing. But I just got back from Japan, and if you pay attention, there are cameras everywhere. So going from the train station to the bus, to the taxi, ATMs, walking around the malls. And similarly in Joburg, all around Joburg are these sort of neighborhood watch CCTV cameras. I actually counted the cameras in one of these stores in Tokyo. And in less than 30 seconds, walking from the back of the store to the front of the store, you can count 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 cameras. And I promise you, no one is watching all that video. And so what I'm going to present today is models that can turn video into useful data. So that squiggly f is a function. I'm sure a lot of you have done some math, and for those of you who are scared of math, a function is really no different than a Python function where you have some input and you produce some output. And you can use deep neural networks to do all kinds of interesting things with video. So the sort of early work on applying neural networks to video perform clip classification. So given a short video clip of maybe like 5 or 10 seconds, the question is, what is in this video clip? Alternatively, you could label each frame of the video clip, remembering that a video is just a sequence of frames. Or you might want to understand like what are the objects in the video and count them, or understand what they're doing in that context, or understand the poses of the objects in a video, or get at the facial expressions, or convert a low-res video into a high-res video, or replace the faces in a video. And really, I want to communicate that you don't need to understand all this really complicated, scary math. And researchers have a vested interest in making math seem scary, and research papers always look a bit scary. But really, if you can clone a repo and copy-paste some code, you can do all these things. So I'm going to give a quick crash course on neural networks, because I find that even if you don't necessarily try to understand how these things work exactly, having an intuition really helps, and it helps you understand the kinds of things that you can do. So a neural network is basically a set of connected neurons with randomly initialized weights and nonlinear activation functions connected in a network that are optimized, aka learned, using training data to minimize some prediction error. So we're going to go through this step by step, and we're going to use this great TensorFlow online tool to do so. So my slides will be online later, and there's lots of links, so don't worry about taking notes or rushing to get this down. But there's this great tool at playground.tensorflow.org that lets you sort of create a neural network in your browser and watch how it learns given some training data. Now, here we have some input neurons and weights connecting those input neurons to neurons in these hidden layers, and we can add and remove hidden layers and add and remove neurons. And we can pick the data set that we're using. Here, it's a classification task where we're trying to classify these two inputs, x1 and x2, into blue or orange outputs. And so we can build this neural network in this browser and train it. Now, a neuron is essentially just a linear combination of inputs and weights. So in the first layer of a neural network, you have some input. In our case, we're going to work towards that input being video. But you have some inputs, and attached to each input, you have a weight, which is a parameter that we're going to learn in this function. And each neuron's value is just multiply the weight by the corresponding input, add this bias term, which is just another weight, sum it up together, and run it through this function. Now, the stuff that's inside the function is linear, and the function itself is nonlinear. And that's how neural networks can learn these complex nonlinear mappings from inputs like video and images into objects and video classifications. Those weights start out randomly initialized. So if we flip back to this TensorFlow example, each time we press reset, it's re-randomizing or re-initializing those weights. These two inputs, x1 and x2, are mapping to these outputs. For every combination of x1 and x2, we have some prediction, which here is either that combination of x1 and 2 is orange or blue. And these activation functions essentially just map this linear combination of inputs into an output. And typically these are squashing functions in the case of sigmoid to tan functions, or just an identity function that says if that linear combination is negative, make it 0, otherwise keep it as it is. And a neural network is just a network of all these neurons combined together in layers. A deep neural network is just a neural network with more than 2 hidden layers. And neural networks learn given some labeled data by taking those randomly initialized weights and updating them in a direction that reduces the error. Now, that's the only equation in this whole talk, and basically it says that we initialize some weights randomly, and the randomly initialized weights might mean that we have an error around there. And as we update these weights to reduce the error reduces. And so if we come back to this interactive example, this loss is another word for error, or cost function is another term that's used, starts off at some value given our randomly initialized weights that convert our inputs into outputs. And as we run this weight update process, given our labeled examples, that loss decreases and our prediction gets better and better. And so if you look at these weights as we initialize them there, it's 0.49. As we run this learning procedure, that weight changes, and these intermediate combinations of the inputs change as well. You'll notice also that this first hidden layer has linear transformations of the input, and the subsequent layers have nonlinear transformations. And you can kind of see, if you blow your eyes, how those two combinations might map to being able to learn a function that's very nonlinear in the output. Now, don't worry if that was a little bit confusing. Basically, before we move on from the deep scary math, TensorFlow gets its name from this idea of a tensor. A tensor is really just a high-dimensional matrix. And so a vector is just a list of numbers. A matrix is sort of like a spreadsheet. We have many columns and numbers. And a tensor is a high-dimensional tensor. We have many slices of matrices. If you look at computer vision, a black and white image which has pixels in width and height, and just whether that pixel is on or off, as in the case on the left, would be represented as a matrix, while the image on the right would be represented as a tensor, where each pixel value is a combination of red, green, and blue. And so if that image was 500 by 500 pixels, 500 height and 500 width, each pixel has 3 color values, red, green, and blue, which together can make any color. And so that image would be represented as 750,000 numbers. Already you can sort of understand why image processing and computer vision can be hard, because that's a very high-dimensional input for most mathematical functions. But when you move to video, you might have, say, 10 frames a second and 60 seconds worth of video, and that's on the order of 450 million numbers. You don't really see pixels too much anymore, but old school TVs, you could see them, and if you look at a smartphone under magnification, you can see that there are these combinations of three colors that together make up the colors in images. So that's a basic neural network. What is a convolutional neural network? Well, the sort of hello world of computer vision and image classification is these handwritten digits, this modified National Institute of Science and Technology MNIST data set. We have 28 by 28 pixel grayscale images. So each image is represented as 784 numbers. And you could use the kind of neural networks that we were looking at earlier to learn these kinds of models that map an image into a classification that says, what is in this image? What digit is this? And if you had a fully connected network like the ones we've looked at, and you took that 28 by 28 pixel image and unrolled it into those 784 numbers, and then connected each of those pixels to just 10 neurons in a hidden layer, and those hidden neurons to the 10 outputs that correspond to the possible digit values, would have 78,400 trainable weights. And this MNIST data set is only 60,000 images. We have more trainable parameters than we have images. It turns out that fully connected networks can do reasonably well on this kind of problem. But if you think about what's going on here, we're taking every pixel value where those pixels appear in the image and learning these intermediate weights that help us to then classify what that image is. But if you move that 4 to another part of that input image or shrunk it, the intermediate hidden values that are learned wouldn't work anymore, basically. Now, the sort of first time that convolutional neural networks started working and appeared in the literature was this paper by Jan LeCun, who's now the head of Facebook AI research, in June 1989. And he was working on a system to read digits, handwritten digits, on postal codes, and then later on bank checks. And he tried several different architectures. So he tried using these fully connected networks. Here, the inputs were even smaller, 16 by 16 pixels, and later versions of these models used the 28 by 28 pixel inputs. And he found that you can get reasonable accuracy. So you can see this test accuracy. That's accuracy on data that the model hasn't seen, but that's sort of like out of sample. You can get reasonably good test accuracy using a fully connected network on the order of like 87, 88%. But there are many trainable parameters. And using this convolutional operation, you can reduce the number of trainable parameters while massively improving the test accuracy. Now, a convolution is really an operation that works well on images and other spatial data that takes advantage of 3 things. So firstly, local receptor fields, shared weights, and subsampling. And the idea is that when you look at an image, you're looking at sort of like local parts of the image. So if you look at that image and you think to yourself, okay, that's a bird, you're looking at the wings, and the pixels around the wings combine into feathers, and feathers combine into a wing, and the wings together make you think that that's a bird. Now, the sort of progression from handwritten digits into models that work today in 2019 has moved from trying to say what is in this image, where it's a digit and a 28 by 28 pixel image, into the kinds of images that we see around us and online. And so this image here shows the ImageNet dataset and classifying images into one of 1,000 categories. Typically, this ImageNet challenge is reporting top 5 error rates. So a model predicts its top 5 best guesses, and if none of those are correct, that's classified as an error. Now, the sort of evolution of the model that worked for images that's easiest to understand is this VGGNet, this Oxford Visual Geometry Group architecture that did really well in this ImageNet challenge. And essentially, it uses combinations of convolutions and subsampling to map inputs into outputs. Now, convolution sounds like a really complicated and scary word, but essentially, it's not much different than if you look in Photoshop or GIMP, there are these filters that transform an input into an output. And so here, this input image on the left, we multiply it by some kernel values in this convolution, this 3 by 3 block. And we can select different kernel values to produce different outputs. And so there, if we select an outline kernel, we can see that the input image is transformed into a sort of outliney image. Or we could select a blur kernel, which transforms the input into a blur. All that's going on there is we're sliding this 3 by 3 block over the image. You can see that red sort of 3 by 3 outline, taking the corresponding values in the input image, multiplying them by the weights in that convolution to produce an output value. And you can sort of see, if you look at the values in this 3 by 3 convolutional kernel, why that might produce a blur versus those values might produce a sharpening of the image. And so a convolution is sort of focusing on some small region of the image, this local receptive field, and is being slid across the entire image. And so rather than learning a weight from each pixel into some intermediate representation, we keep the weights the same on that convolutional kernel and slide it across the entire image to produce an output. And so to go from that input to that output, you only need to store those 9 numbers. In a convolutional neural network, those 9 numbers, rather than sort of thumb-sucking them to produce a blur or a sharpen, are learned given labeled training data. And this VGGNet, if you look at the hidden neurons in that architecture, like in the TensorFlow playground example, you'll find that in the first layer you have linear activations, and in the deeper layers you have these nonlinear transformations that go from an input into detecting sort of like eyes and wheels, and ultimately being able to classify animals and objects in those images. And so essentially convolutional neural networks learn hierarchical features. They also use the subsampling operation that takes moving windows of the image and computes the max in that image or the average in that region to produce a low resolution intermediate value. And so this VGGNet architecture is just stacking many layers or feature maps of convolutions from an input, and then subsampling layers, convolutional layers, subsampling layers into those 1,000 ImageNet categories. And implemented in Keras in less than a page of code. And so this training data, as I mentioned, that's typically used in these convolutional neural networks is this ImageNet dataset, which is a dataset of around 15 million images and around 22,000 categories. This ImageNet large-scale visual recognition challenge, the ImageNet competition, is a subset of that data with 1.2 million images and 1,000 categories. And these images are not sort of consistent with the subject in the middle of the image, like in those handwritten digits. These objects are photos taken, or these photos are taken at different angles, different levels of zoom, and it would be really difficult to sort of hand build a model that would be able to tell you what each of those images is. Whereas by learning these intermediate transformations of the inputs using these convolutional layers, we can just input a large amount of data, create an architecture that is learnable, and learn these intermediate transformations. If you look at the top 5 accuracy on this ImageNet dataset, until 2011, these models were using traditional image processing methods where you'd like sort of hand design these feature extraction methods that take an image and convert it into a lower dimensional intermediate representation. And this is top 5 error rates, so none of those 5 predictions were correct around 74% of the time in 2011. Then in 2012, the first deep neural network model reduced that error rate by around 35% relatively. And since then, the accuracy has gotten sort of exponentially better as these models have gotten deeper and deeper. And so the 2017 top 5 error rate was around 2.25%, and human level accuracy on this task is around 3% error rate. So these models are sort of at human level accuracy or better now, and this ImageNet classification challenge is no longer running because it's considered almost like a solved problem. Now, to go back to this idea that you don't really need to understand all this complicated math, and I think the intuition helps to make it less scary to use these kinds of models. You can use this library called Keras to take any one of these architectures that has done really well on this ImageNet data set and use it for yourself. And so here you can see the top 5 error rate of those architectures and various versions of them. And I'll go through this example very quickly. I went through it in more detail in a previous talk, but basically taking images of clothing and classifying them into one of 8 categories. Now, to use a pre-trained convolutional neural network, that's all you really need. And so there on line 6, we import this ResNet model trained on ImageNet. Line 7, we load an image and transform it, like resize it into the size that that network takes as input, and then run these predictions. And so given an image of a Python, Python is one of the categories in ImageNet, and so this model predicts that image as a Python. If you run it on the logo of this PyCon, you get shield as one of the predictions, which I think makes a little bit of sense. Now, if you use a pre-trained ImageNet model on those 3,500 odd images of clothing and try to classify them, you're limited to the categories that are in ImageNet. And we don't want to predict one of these 1,000 categories. We want to predict one of those 8 clothing categories. And so we can use this idea of transfer learning. And really, this is sort of viewed as this process of using a convolutional neural network as a feature extractor. And so we take an image, run it through this model, and instead of running it all the way into the 1,000 predictions, we can take one of the intermediate values and use that as a sort of like feature representation, and then learn a new classifier instead of using the classifier that goes from that intermediate representation into the 1,000 categories. We can learn a new classifier for the task that we care about. And extracting features from an image is sort of as easy as using a pre-trained model. Instead of including the top layers of the network, you just use this include top equals false option. And so you can load one of those models, add a new classifier on top, and here this model has 8 neurons in the output layer for our 8 clothing categories. And training this for less than 2 minutes gets us to around 96.3% accuracy on classifying those 3,500 images into categories. And like really copy-pastable. There's a more in-depth tutorial there that you might want to check out. But this idea of converting an image into a feature vector is really interesting and important. And if you want to take a video and classify what's in the video, you could just run a image classification model on the frames of the video. For example, if you wanted to detect whether there is, say, for example, like nudity in a video in an image or video moderation context, you could just run an image classification model on the frames of a video. But if you want to do action recognition or something like that, you might need to take into account the sequential information in the video. We'll come back to that shortly. But so object detection, unlike image classification says, what is this image out of a defined set of categories? What is this? And is it a cat or a Python? Object detection answers what are the objects in this image and where are they. And intuitively, you can think about this in terms of breaking up an image into different regions, running a classifier in each of those possible regions, and then if a certain rectangle of that region has a very high probability of being a dog, then that's a dog. Practically, the state-of-the-art models today use a fully convolutional approach to sort of like speed up the inference and can be used sort of real time on the frames of a video. Object detection, unlike image classification, needs to be trained on a data set where you annotate where objects are in the image. And there's this open source Coco data set with 1.5 million object instances across 80 categories. And just like the ImageNet case for classifiers, you can download these pre-trained models. and use them for yourself. So I've got a quick demo that we can try. Probably pushing my luck here, but not great, but not bad. So detecting a person, there's detecting a cell phone. And even if you didn't follow anything that we've been through so far, again, if you know how to copy-paste code and know what to look for, you can use these pre-trained models for yourself. And the model that we just looked at was using this pre-trained model on Cocoa. Like the image classification example, we don't want to classify objects or detect objects limited to those 80 categories in Cocoa. We might want to detect trucks in a mine or something like that. And training a custom object detection model requires us to annotate some data, just like in the image classification case where we put images into different folders. You can use this tool called label image to make this easy. And there's a few great tutorials out there that go through this, but really it's a matter of labeling your data set, taking a model that was trained on Cocoa and then fine-tuning it. So rather than needing millions of images, you need on the order of a few hundred or a few thousand images per category, and you're using these feature extraction hidden layers in these models that have been trained on other data sets to make it easy to train models on new data sets. Now, one common task that you'll do in a sort of like video processing context is license plate recognition. A license plate recognition model, an easy way to build one is to build an object detection model that detects license plates, then crop to the license plate and detect characters, and then crop to the characters and classify that character into your alphabet of possible characters. We've done some interesting work in mining where trucks are supposed to come over a weighbridge and they're not supposed to take a bypass road on either side. So it's allowed to go through those two concrete barriers, but it's not allowed to take a side road. And normally a security guard is watching what's happening. And also the truck is supposed to only take the product that they've paid for and not a different product. But instead of giving the security guard an order number when they enter the site, they give the security guard like a few $100 cash and go inside, or they'll take the bypass. And there's all kinds of fishy business going on. And so using these kinds of ideas, you can build a system that doesn't require a person to watch what's going on, but can track objects as they come in, or in this case, vehicles, and then triggers a real-time alert if a truck takes the wrong bypass road, or if a truck enters without an order, sending real-time SMSs, using these sort of object detection models, then fine-tuned and labeled on and trained on custom data sets. Also with an interface to sort of give feedback if the model makes an incorrect prediction. We've also done some interesting work in transport. This is really good with the sound because you can hear them counting people as they come out of this taxi. Crazy and sad. Basically, there's 42 children in that taxi, and you can see them. It's a lot better sound because you can hear the cops like shouting angrily. But all those people were in one taxi. That's 42 children in one taxi, and so using an object detection model running on cameras at taxi ranks, you can count the people getting in and out of taxis where this kind of thing wouldn't be feasible if you had a person needing to count people getting in and out of taxis all the time. And so we just detect people, detect the taxi, And then if the person disappears inside the taxi, increment the in count. If the person appeared inside the taxi and disappeared outside, increment the out count. And if you can train a object detection model that can detect people, to track them between frames is just a matter of computing the centroid of each of those object detections, figuring out which object is nearer, and then creating consistent ID between them. You can also use those sorts of ideas in traffic control in other interesting ways. Here, counting cars going through a part of the freeway and calculating average speed based on how fast they move through a defined region, or detecting parking when parking spaces are full or empty. Now, all the approaches that we've looked at so far operate on video frames in isolation or images in isolation. But video contains motion information. And so where a convolutional neural network is a special kind of neural network that takes into account these local spatial correlations that are inherent in objects in the real world, recurrent neural networks work well on data that has a sequential nature. Now, again, you can use a fully connected neural network to classify something like actions that people are taking. So this is a data set of actions people are taking at a train station, and in some cases, a person is leaving a package, and the obvious sort of like security applications here. And prior to deep learning, you would run these hand-built feature extraction algorithms and build these models on a frame-by-frame basis, and then combine these frames together. Early work applied these ideas of convolutions, but instead of running a convolution just on the spatial two-dimensional part of an image, you can run them on this three-dimensional width, height, and time depth of an image. And that works reasonably well, but much better is to use these models that have been trained on massive image data sets and then add a sort of like time series component on top of them. And so there's this interesting work from 2012 where under Kapathy and a bunch of collaborators created the sports 1 million data set by scraping videos from YouTube and sought to classify what action is happening in those videos. And the model that they found to work much better than classifying frames in isolation, one approach might be, let's say you have a 10-second video clip, you just sample frames at 1 frame per second, you run each of those frames through an image classifier, and if 7 of the 10 frames think or predict that the action is baseball, then say the clip is baseball. Much better is to run each of the frames through a convolutional neural network to extract features, and then use a recurrent neural network on top of those features to encode this time series dimension of the video. And so just like you can use a convolutional neural network to convert an image into a vector, you can use a recurrent neural network to convert a time series of vectors into another vector, this feature vector. And they did some other interesting work on the video side in captioning the videos by combining these time series of video frames run through convolutional nets with a language model. We've done some work in ecology on detecting seals in video camera traps. And if you run a model that just operates on frames at a time, you get a test accuracy of around 71%. But if you take into account the motion dimension, you get a much better accuracy of around 93%. Because seals move a certain way and seaweed moves differently. And this camera trap approach is one interesting approach in ecology. Also interesting are these cameras sort of attached to animals to see through their perspective and analyze animal behavior. I don't think they really like it because, there are cases of seals throwing octopuses at people kayaking. But these sorts of approaches let you understand animal behavior in ways that you otherwise couldn't, because animals change their behavior under human observation. And so there have been all kinds of interesting results, like seals have been found to blow hot air under the ice to sort of shake out fish that are burrowed under the ice, and it's a hunting behavior that was never known. And there are all kinds of studies that happen in ecology where people capture video from an animal's perspective to understand their behavior, but normally, these studies are conducted by having a graduate student sit and label, like from 3 seconds to 12 seconds, the penguin is above the surface. From 12 seconds to 15 seconds, it's descending, then it's ascending. And you can sort of see by looking at those different examples of categories why the time dimension of this data matters, because ascending and descending look the same in isolation, but the sequence is how you tell them apart. And similarly, there's an example of this video data. You get a much better accuracy using these recurrent models over these convolutional models that extract features. Again, though, you just need to be able to copy-paste to use these kinds of methods. So a few more crazy applications. I really like this example from the TensorFlow Summit in 2017, where Francois Chollet, the guy who created the Keras library, shows this video question answering model. And so you have a large number of videos, and you want to be able to ask a system questions like, what color is the woman's shirt? Or what is the woman doing? Now, the what color is her shirt question, you don't need to consider the time dimension. You can just look at these frames in isolation. But if you want to answer what is she doing, packing and unpacking look the same in isolation, but taking into account the time series component makes all the difference. Also remarkable is this architecture, like the sports one that we looked at earlier, where they first use a convolutional net to extract features from video frames, and then a recurrent model on top to create a feature vector from the time series of frames, can be implemented in Keras in, again, less than a page of code. These face swap models are a little bit more complicated, but not all that much more complicated. Essentially, given two examples of faces, use the same convolutional encoder, but learn a different decoder for each. And so to then run this face swap, you first crop to the faces using an object detection model, feed an image into the same shared encoder, but the decoder from the second image. Again, though, if that doesn't make any sense, just copy-paste from GitHub. Really crazy result that came out a few months ago. Rather than needing hundreds or thousands of images to be able to train these models, these guys came up with a model that uses very few examples to create realistic talking head models. And so here, you can see the results given just one image versus 8 images of creating a talking head model from an image. Or put more concretely, given one image, you can create a talking head model from those images. This uses a similar kind of architecture, again, using a convolutional network as an encoder that sort of captures these hierarchical local features and images. And again, you can just pull that off the shelf and use it to encode an image, together with this generative adversarial network idea, where you have one model called a generator that tries to generate or synthesize images from landmarks, and a discriminator that tries to tell whether that synthesized image is fake or not. And these sort of compete, and all three models will learn together. Also, rather than sort of detecting an object in terms of where the object is as a bounding box, you can detect the actual pose of objects in the image. And this isn't all that much more complex than detecting objects in images, where here you're detecting different aspects of a person's pose. These poses are then combined using this histogram of oriented gradients idea, and then this greedy step to combine the detected body parts into individual humans as poses. Once again, though, if you know how to copy-paste code from GitHub, you don't need to understand any of that, and you can just use it for something interesting. And yeah, all kinds of interesting applications. For example, distracted driving. The last sort of example I'll mention briefly is using video cameras on self-driving cars to hopefully avoid pedestrians and collisions. Elon Musk made the statement that anyone relying on LiDAR is a kind of like depth sensor that's very expensive, that goes on cameras, is doomed. Experts say maybe not. He has an agenda because Teslas have lots of cameras, but they don't have these expensive LiDAR sensors. And this is again where some of the hype around like deep neural networks and AI taking over the world meets reality, because Waymo or any of these self-driving car companies need these very expensive, very computationally intensive sensors, but a person can drive using only their eyes and a much low power brain. Remember that really all that a deep neural network model is a function that maps some input to some output. In this case, we've looked at mapping video into some useful data. It helps to understand what's going on, to sort of demystify and make it less scary. But it's all out there, and there are a bunch of great free resources that you can take a look at if you'd like to understand it in more detail. Otherwise, feel free to send me an email, and I'd be only too happy to help and nerd out about some of this stuff. Thank you. I understand if any of you wants to leave, because it's like 2 minutes to 5, but I will stick around if you want to ask any questions.
Yeah, I think we have time for maybe a couple of questions. Anyone? Going to wait for people who've asked me fewer questions. Anyone? No?
Yeah, there's no place like home.
So I was waiting for the mic. The mic is come on. Okay. The question is, very few cars are rectangles.
Yes.
Okay, but your classifier earlier was picking up rectangles for everything. How close are we to something that can pick out just the car and not a rectangle containing the car?
A few years ago, so I feel like I went a bit too deep in general. I didn't want to go even deeper and go into pixel segmentation, but instead of drawing a bounding box around an object, if you want to predict each pixel to then be able to draw a clean contour around it, that's called image segmentation, and there are models like these that you can clone and use to predict pixels instead of, I mean, this self-driving car video that I had here, sorry, hot corners, predicts pixels, not bounding boxes. So, yeah. Yeah.
Yeah, and one at the back.
So I've got 2 questions.
Yeah.
The first is projects for recognizing faces. I know there is one that classified, and we're actually using it, faces into a 128 vector basic spatial representation, and you do a distance. I don't know if you know about that and know about the accuracy of those projects. And then specifically with regards to, I think, different groups, because these things were trained in America, whether it will work on our local populations, specifically black people and Chinese people and things like that. Then the second question is, do you know if any of this will run in WebAssembly on JavaScript side, or is this mostly on the Python side?
Yeah, great questions. So yeah, we have some experience playing around with some facial recognition work. It depends on how you're extracting the features from these images. I mean, if you can crop to a face, you can run it through any feature extractor you want. The feature extractor, that VGG feature extractor we looked at, will produce 25,000 dimensional vectors or 4,000 dimensional vectors. You can use any of these pre-trained models that you want. Generally, those kinds of feature extractors tend to underperform feature extractors that are trained specifically for faces, so these facial landmark extractors. That OpenPose repo has a model that works better, for example. But if you subset your data set into sort of Western faces and African faces, it works much better on the Western faces. That's not to say, though, that you can't realistically label a data set of facial landmarks on your own that would work reasonably well. And the Cocoa data set, for example, looks really big and it's getting really amazing results, but you could pay people a fair wage and get a data set bigger than that, in a month with a few people working in parallel. So if you're serious about it, you can learn your own feature extraction models that work well in all contexts. As for WebAssembly, there's TensorFlow.js that works in the browser. I've only played around with it very lightly, so I can't really say how well it works. But it seems to work as well as running it locally. A lot of the inference that you see for this real-time self-driving cars and deep fakes is running on GPUs, and so I wouldn't expect that to work that well in a browser, even if you do have a GPU. But certainly you can do a lot of the object detection stuff. Those inferences are on the order of milliseconds, so even if it's a little bit less fast, I think it'll run well in the browser.
Cool,
Yeah.
and I think this will be the last question.
Cool.
Hi, Alex. Great talk. My question is around accuracy, because I noticed that reCAPTCHA keeps telling me to tell it where the traffic lights are. So the accuracy is getting better, but if I were to use a machine learning model, are there ways to know when something wasn't accurately classified, or do I just kind of have to eat the inaccuracy somehow, just accept that some of it's going to be wrong? How do you deal with that?
Yeah, so models don't predict they don't produce a prediction, they produce a probability distribution over predictions. And so if the model says that it's 75% sure that this image of a python is a python, then you can map that probability prediction into some kind of confidence that would be less than if it was 99% sure that it's a python. And generally, in the real world, when you build these kinds of systems, it usually helps to have a feedback loop where you say, for example, we did a whole lot of work in image moderation at scale and video moderation, and there, originally, this company was one of the biggest online dating companies in the world, had a team of people whose job was to sit and manually moderate images as they came in. I mean, I know Facebook has tens of thousands of people whose job all day, every day, is to moderate images. And rather than having people moderate every image, you can run your image through a convolutional neural network or your video through a recurrent convolutional net and have it produce a prediction. What is the probability this image or this video contains nudity? If that probability is, say, greater than 50%, maybe you want to auto-reject it. If the probability is between 10 and 50, maybe you want to show it to a person. And then you have a feedback loop where you use the person's prediction to then update your models so that over time your models get better. But certainly I wouldn't recommend just trusting the models. And it also depends on there's often these asymmetrical payoffs where in the image and video moderation case, this company was making all their money on ads, but they want final warning from the social networks where you're not allowed to show ads alongside nudity, and so that's why they had people whose job was to just make sure there was no nudity. You'd upload an image, it would appear to you as though it was uploaded, but actually first person would have to give it the okay. But in other situations, like if the model makes a mistake, it doesn't cost that much. It's not like all your revenue is going to go away, and so it depends on the situation. But you can use the confidence to decide when to have people as humans in the loop. Yeah. I'm going to stick around if anyone wants to ask any more questions.
Yeah, so if you have more questions, Alex was happy to answer some more afterwards. Thank you, Alex, for a great talk.